Okay, now we're going to be talking about heterogeneous equilibrium. For a heterogeneous equilibrium, what that means is that not everything is in the same phase. As you can see from this equation here, the ammonium chloride, NH4Cl, is a solid, whereas the NH3 and the HCl are both gases. So pure solids, pure liquids, and water, by the way, is a pure liquid, do not appear in the K expression. The position of the equilibrium is independent of the amount of solid or the liquid present, as long as at least some is present in the reaction mixture. So they just have to be there. So that simplifies greatly some of the equations that you have to work with. Okay, so nothing further on that. Let's talk now about the Le Chatelier's principle. A system is at equilibrium, but then that equilibrium is disturbed. It's going to return to equilibrium by counteracting that disturbance. So if you add something more to one side of the equation, that will force it to the other side of the equation. So whatever that disturbance causes a change in the Q, the reaction will shift to reestablish so that Q is again going to equal to K. So you can do this by adding or removing a reactant or a product. If a chemical equilibrium is disturbed by adding a reactant or product, the system will proceed in the direction that consumes part of the added species. In other words, if you add more of your reactant, it's going to move towards the product. If a chemical equilibrium is disturbed by removing a reactant, such as when a precipitation takes place, the system will proceed in the direction that restores part of the removed species. In other words, it will go back towards the reactants. The system responds in a way that restores equilibrium and therefore allows Q equal to K again. So adding or removing pure liquid or solid has no effect on the system unless all of the solid or liquid is removed. This is because pure solids and pure liquids, all solids and pure liquids do not appear in the equilibrium expression. And that just gives you an example with bromine. So another way you can shift that equilibrium is by increasing the temperature. If you increase the temperature, you increase the heat. The equilibrium responds in a fashion that consumes that added heat. So by changing the temperature of a system results in a change in the value of the equilibrium constant. If the forward reaction is exothermic, K decreases as T increases. If the forward reaction is endothermic, in other words, takes on energy, then K increases as T increases. So, in other words, in the first example there, forward reaction exothermic, K decreases as T increases. So you increase the temperature, decreasing K means that it's moving back towards the reactants. If it's endothermic, adding that additional temperature is pushing it towards the products. Hopefully that's clear. Now, you can add a catalyst and it will speed up the rate of reaction, but it does not cause it only causes the equilibrium to be reached more quickly. So it increases the forward reaction and the reverse reactions, right? But a catalyst does not affect where that equilibrium concentration or value of the equilibrium constant. This gives you an example right here, where you've got the energy, and this is an exothermic one. You are going from the initial energy level down to a much lower one. Okay, so energy is going to be given off by it coming to that level. But it has that hump in the middle, right? What that means is that it has to be activated. It has to get up to that level before it can go to the products. What happens with a catalyst is you're essentially bringing that hump down lower so that the forward and reverse reactions are less. So you can see from this that the E forward and the E reverse are shifted downwards, but there still is an activation energy reverse and an activation energy forward, and so there is still a hump that needs to be overcome. One of the very famous ways in which you do this with the help of a catalyst is the Haber-Bosch process, which is the commercial production of ammonia. Very useful for production of ammonia, which is then used for making a whole lot of different fertilizer products. So let's talk about equilibrium calculations. You can calculate an equilibrium constant by looking at what the different concentrations are when you finally reach that. Also, if you are given missing equilibrium or concentration or partial pressure, you can use the other values there and knowing what that equilibrium constant is to determine what concentration would finally result. Likewise, you can calculate those from initial concentrations. For example, in this equation we have iodine, I2, plus an iodide ion, I, with a minus up there, forming the I3. And the initial concentration of both the reactants is 1 times 10 to the minus 3. And of course, there's nothing for the product. So because of the coefficients in front of this, for every mole that's consumed as a reactant, in other words, a decrease of X causes an increase in that same number of moles on the product side. But there's a minus X for both I2 and a minus X for the iodide ion. So if you have there that the equilibrium concentrations are 1.0 times 10 to the minus 3 in each case, you can then determine what those are. So what's going to happen is you are going to, if you have that decrease, a simple subtraction of that number from your initial concentration gives you what the change is. And then you can see both I2 and the iodide ion both change by minus 3.39 times 10 to the minus 4. And but there's only a plus 3.39 times 10 to the minus 4 for the other one. You can then plug those in to the K equals 3.39 times 10 to the fourth in the numerator, and then both 6.61 times 10 to the minus 4 and another 6.61 times 10 to the minus 4 are going to be in the denominator. And you can see this is example 13.7. And this particular type of table is called an ice table. It's called that because it starts with the initial concentration, the I. The middle row is called the change, the C. And then the final one is the equilibrium concentration, or the E. So it's an ice table, right? And from this, once you know certain values, you can always calculate your missing components. And usually you're given either the equilibrium constant or you determine that equilibrium constant. Now there's a couple of special situations. In this particular one right here, you have the initial concentration going to two different products. Okay, so here's every drop in PCl5, that's phosphorus pentachloride, gives you one of the phosphorus trichloride and one chlorine molecule. And so when you work this problem, what you'll find out is, and the example that they have is 13.9 on this, and this is on page 756. The K value here, they give you in that example, is 0.211. So when you are solving for that with this one, you end up with something that's quite a bit more complex. And you have to use a quadratic equation in order to solve for what the value of concentration of chlorine and phosphorus trichloride will be. And they work that out there, and one of the key points to note there is when they are solving that, only the positive root has any value, so that x equals 0.135. And so when you substitute that in there, both the PCl3, phosphorus trichloride, and the chlorine molecule will end up with a concentration of 0.135, and then the phosphorus pentachloride will be 1 minus that, so that will end up being 0.865 moles. Your book rounds it up, but they really shouldn't, because you've got 3 significant figures here, and we all know how we have to react to those significant figures. Now there's a special case as well, and here what you've got is one where the initial concentration is 0.15, but the key thing here is that the K sub C value here is 4.9 times 10 to the minus 10th, a very small number. So that when you multiply the denominator, the 0.15 minus x, times that, you're going to end up with a very, very small number. And so when you work out with a quadratic equation, the x squared is going to be extremely small compared to the 0.15. So in these instances, what you can do is you can just ignore portions of that, and you end up with Kc equals x squared divided by 0.15 molar equals 4.9 times 10 to the minus 10th. Therefore, x squared is going to be 4.9 times 10 to the minus 10 times that 0.15, or 7.4 times 10 to the minus 11th molar. And then you take this, but that's x squared. The square root of that is 8.56 times 10 to the minus 6. And so if you were to do a regular subtraction of 0.15 minus 8.56 times 10 to the minus 6, you can see that that's way far out there, and your assumption is very good for being able to ignore that. So that's the end of chapter 13, and we'll then begin the next segment with chapter